Welcome back, Gen Chem friends. So in the previous videos, we have explored several mathematical expressions that describe gases with respect to volume, temperature, pressure, and moles of gas. Those expressions, since they all have a volume in common, can be grouped into one expression, which is what's done down here. That directly proportional sign can be replaced by a equal sign if we do a little bit of algebra with some constants, which is what I've shown here. And that can be very handy because if I can say that the pressure and the volume divided by the number of moles times the temperature of a gas, if that is a constant, and if I have initial and final conditions of that gas, I can do some algebra and say that the initial pressure times the initial volume divided by the initial moles times the initial temperature is equal to the final state of that gas. More commonly, this, especially if you are dealing with the same gas with number of moles constant, this expression devolves into what is commonly written as the combined gas law. P1V1 over T1 is equal to P2V2 over T2. So this combined gas law is very convenient to use if you have a gas and two variables are changed, such as in this example. So let's say you're a meteorologist doing some weather experiments. You've got a helium-filled weather balloon. It has a particular volume at a particular temperature and a particular pressure. So I have let me get my pen, I have a P1, I have a P1, I have a V1, and I have a T1. It's released and rises where that new pressure, so I have a P2 and I have a T2, and I want to know what the new volume V2 of the balloon is. And so seeing the variables that you're given, the data that you're given, using the combined gas law is what is going to be useful in solving this problem. And hopefully you've realized that, in organizing your data, that, well, I have to convert my temperatures into Kelvin always and forever. Amen. But my pressures, since my pressures are both in the same unit, I can be somewhat lazy and I'm not going to go ahead and convert those into atmospheres, because when I substitute those into my combined gas law equation, the units will cancel and I'll still get a volume that is in liters. You would still get the same answer for this problem if you converted both of those pressures to atmospheres. But since they're both in millimeters of mercury, I'm just going to stick with that. So I've organized my data. I need to solve my combined gas law for V2, which I've done neatly down here by cross multiplying and dividing from what's in the blue box. I then substitute the appropriate values in, number and unit. I see that my millimeters of mercury units cancel, my Kelvin cancels, I'm left with liters. And so doing the multiplication and division, and I'm not going to be picky about sig figs so much, but since I had data that was in 3 sig figs, I went ahead and reported my answer to 3 sig figs, which is 1.21 times 10 to the 3 liters. So the combined gas law, very useful to use when you have a gaseous sample, and more than one variable is altered. One other thing I'll note, this 4.56 kilometers, did we use that at all in the problem? Nope, that was just extraneous. So I think it can be helpful when reading word problems to do little charts like I have done here and like I'll do throughout my videos to make sure that I use only the information that is needed to solve the problem.